Okay, so recall you have the Schrodinger, and I should say versus Heisenberg. Schrodinger versus Heisenberg pictures of time evolution, where you evolve states, and again using that funky notation of the book. And in Schrodinger, which I like, in Heisenberg, time evolves the operators. I certainly think of states evolving in time. That is absolutely sensible. But as I've hinted, I look at this and I'm like, what the heck are you talking about? But as I've hinted many times, it's because you get relationships like this. Again, I'm previewing, and that handout I sent you actually does this problem, which I'm technically doing today. So, initial position plus velocity times time. That's pretty important, sorry. Times velocity, times velocity is how you change position. So this certainly has an appeal too. Okay, so when we did the Schrodinger picture, what we did was we had, and I know I butchered this one, because I started doing it one way, and then I switched from a representation of the z plus minus basis set, and I switched to a representation of the x basis set, or vice versa. So if you got a little confused on that, I kind of owe you a handout on how we did this. And of course, what I mean, of course, is time evolved. Sorry, and so I'm obliged to put this in the full parlance of the textbook. And what this ended up being equal to was, S? I'm speaking out of my rear end here. Squared, or minus, I forgot. Let me double check this. I've already, that's X minus, yeah. Okay, there we go. And this ends up being okay. Now, heads up. The reason I just remind you again that this is the time-dependent expectation value of spin in the x direction. And again, I kind of butchered this, but that was the result. Heads up, guess what I'm going to do today? I'm going to do the same problem in the Heisenberg picture, because it's a good exercise. Remember also that it also shows, I know I harp on this too much, but eigenstates don't evolve in time, which is just the most bizarre thing, because we think of everything as being like in the ground state. Now, of course, one way to not be in the ground state is to perturb something, and of course you do that by switching from, you can perturb things by perturbing them. In a proton in the magnetic field, the proton's magnetism is aligned with the field, but you can hit it with radio waves to point it in the positive x direction. And all of this is then the quantum mechanical solution to that, and I've said that before. And then, again, we're going to go into more deeper ways to think about why things evolve in time. Just one of those things I'm just obsessed with. Okay, anyway, so I wanted to remind you of that. And Sy, this was complex. At time 0, this is h bar over 2, but I set up the problem such that initially the state was rotated into the Sx plus direction. So because it's rotating, right, precessing is the scientific word. then it will turn into the SY plus and minus direction, just 90 degrees out of phase. Let me point out one other thing. Now, maybe blowing your head off here, and I don't want to do that, but I do want to point out something. You might recall when we were solving what SX plus and SY plus and yada, yada, yada. When we were solving what that was, at one point I put in a phase factor. So maybe don't write this down. Don't write this down, but you may recall that I did something like this. I said that I don't know what, I had some symbol, and then I said SY plus or minus something. Anyway, I kind of forgot what I did, but it was something like this. No, not minus, just okay, do you remember that we did that?
Yeah.
And somehow we figured out that these, if we set one of these to 0, that the other angle, we solved for the difference in the angles, and it was pi half. So if this was, if this angle was 0, e to the 0 is 1, and then that made that I. Imaginary number. Okay, the reason I'm bringing this up is, remember I said that these are called phase factors. They don't really do anything because the absolute value of e to the I anything is 1. They never do anything. So why would I ever bring this up? It's because here, remember that all of this works out the way it worked out because I bent the thing over into the plus x direction. But if I had altered the phase relationship between these two, then it may have actually been, I could have done this. Right? I could have bent it over, not fully into the positive x. I could have bent it into the positive x, negative y direction a little bit, right? The time evolution, it wouldn't have been cosine. It wouldn't have like it may have been cosine, but it would have been frequency time plus some kind of offset, and then the same here. So what I want to point out is when I did this so long ago, even I was thinking like, why the hell am I doing this? Now I actually didn't know why, but anyway. It looked like it was kind of crazy to do this, but the reason it matters is because time evolution is affected by phase factors. And that's also, unfortunately, very hard to see. I mean, if you look at, I think your textbook says that at one point, but it's like, okay, you know, it's like Einstein's theory of relativity affects the motion of Mercury. It does. Mercury's orbit around the sun is a little wonky. And the only way to understand that is to use Einstein's theory that gravity bends space. It's not Newton's. Mercury does not fully follow Newton's laws for gravity. It follows Einstein's laws because there's a subtlety in its orbit. Okay, so when I say Mercury's path is due to Einstein's theory of relativity, you probably kind of nod your head, but it's like, so what? You know, you don't really get much out of that, right? At least I don't. I mean, I understand that string of words, but the deeper meaning, I don't even have the slightest clue. So when I find that when the book says phase relationships matter in quantum mechanics, I always felt the same way. Okay, I know what those words mean, I just don't really know what they mean together. This is what they mean together, right? The phase, in the sense of preparing a state to evolve in time, I didn't have to put it in the plus x direction. And as a result, that would not have been cosine or sine, or they wouldn't have been exactly the same thing. That's the result. That's why the phase relationships can affect time-dependent quantum mechanics. Maybe, you know, if I'm being horrible, maybe I'll even work a problem like that on the take-home exam. I'll see how, I mean, I know it's doable, it just depends on how hard it is, and I don't even know how hard it is. So, but maybe I'll look into that so you can see that that is the case. Anyway, I just wanted to point that out because I know it's made it seem like, well, what the hell am I doing this for? Anyway, all right, so let's go forward. The mission is to reproduce this with the Heisenberg picture, with the Heisenberg equations of motion. And what we got to last time, I have to find it, where we at, is, so as soon as I put a parenthesis with T, that means I'm working in the Heisenberg representation. Okay, so I solved this last time, and yeah, all right, so, oh God, what do I want to say about this? I did want to point out that, sorry. Again, you know what, just forget this. Just on your homework, I wanted to point out that I did give you an example. Right, so you had to work with this thing. This is okay. And what this is, by the way, this is an alternative way to solve the Heisenberg time-evolving operator. So in my class, we spent like 5 minutes doing an example, but I've already wasted too much time even today. So when you need to evolve this operator A, obviously you have these unitary operators on left and right, and that expansion that you have on problem 1 is one way to do the time evolution of the operator. Unfortunately, the way you get into these nested commutators is like awful. So it can be. There's some examples, like the example that we did when I took this class, it wasn't that bad. Another time I'm sure it's intractable. Regardless, this is the other way to do it, and this is basically how you'll see it done. So I just wanted to point out that the reason I had you do that homework question is just I wanted you to see that identity. It actually is useful for something. Obviously, B is the Hamiltonian, and lambda is I over h bar times t. So anyway, that's why that problem existed, but let's do this one. All right, now what? Now, one of you, yeah, right there, he asked me a question at the end of class, which I appreciated, which was, how did you ask that? I wanted to point out that if you're evolving the Hamiltonian, if you have a time-dependent Hamiltonian, which is generally true, what am I doing? Yes. Well, actually, I need to do it the other way. If the unitary operator, I'll do this one. If this equals to 0, then you can do, what have I done? I need to be consistent. It doesn't matter which way you go, but okay. So, and I should have had a little H0, right? So this is just the Hamiltonian like we've been doing the entire time up until literally last class. Okay. So, and so what I'm saying here, I've given a nice slick little thing here. But Abdul actually asked me a question. He pointed out something, that the answer is fixed. Okay. So what's happening is, when we solved this unitary operator using that Dyson series, that thing I told you, I have only seen it even brought up once in a professional talk. that Dyson series, that hideously long across the board, like a million integrals, was when you have a time-evolving Hamiltonian, like you put something inside of a rotating electric field. If not, then the unitary operator turned into this. For a time-independent Hamiltonian, this is the unitary operator. So how could this not happen? Right? I've used this. This is a function of the Hamiltonian. So a function of an operator and the operator always commute. That's impossible that they don't. No matter E or x squared, whatever. But this operator is only what this operator is because I already said the time, there is no time dependence to the Hamiltonian. So guess what? It worked out. Okay. Now, the reason I bring that up is you can still have a time-dependent Hamiltonian in the Heisenberg equations of motion. And if you do, that sucks because that's going to be really hard to figure out. In fact, I think you would want to be using the Dyson series instead of this. This is like an alternative approach to doing time-dependent quantum mechanics. So if you truly do have a time-evolving Hamiltonian, you probably aren't going to be taking this approach. Anyway, so I just wanted to point out, because I did this slick approach to show, oh, look at this isn't so bad. Again, the time zero needs, the simplest, the thing we've been doing this whole time. But then Abdul pointed out that I've already presumed a time-independent Hamiltonian because this proof only works on a time-independent Hamiltonian because when we did time dependence initially, this was only true for a time-independent Hamiltonian. So I appreciated that. It's just funny. It kind of bothers me, like how we also we worked out the time-dependent Schrödinger equation using the operator, and I said, but that operator, the time evolution operator is 1 minus I Hamiltonian T over h bar. That comes from the time-dependent Schrödinger equation. So you have a chicken or egg situation. Which came first? You're using an equation to prove itself. That's always going to work. So anyway, sometimes like for undergrads, I'll do that. I actually will intentionally trick them because then they're like, oh, okay, everything works. I'm like, yeah, it had to work out, Anyway, so I digress. Okay. So again, we're going to work on this problem, and we're going to have a time-independent Hamiltonian. I realize that the reason I'm especially went off on this is as I was reviewing my notes, I don't think I'll get to it today. I do have one example of a time-dependent Hamiltonian. Okay, now let me also point out that the Bisnacker here is, let me write this down again. Okay, so the reason that we run into a slight problem here, commutators, now often, guess what? Often these are going to turn into x and p, which is I h bar or minus I h bar, I forgot. Heads up, that's the clever thing that's almost always going to happen. And then this is a differential equation, but it's a first order differential equation, which are always like child's play. Bring the dt over and integrate both sides, and integrals you learned in first semester calculus. So that's great, but until we whittle it down using all our tricks that are coming to show that this is basically always x and p, until we do that, on the outset, I'm like looking at this and I'm like kind of PO'd because here is what I'm trying to solve. All I have to do is I need to know what the commutator is, but it involves the thing I'm trying to solve. So what the hell do I do with that, right? It's like unsolvable as it's written. Of course, again, as I've already said a zillion times, there's slick willy ways. Every problem that you have has a slick willy way of getting around that. Okay, and so we're going to do two examples, and of course, for the spin problem, let's write our Hamiltonian like we did a little while before. So technically, remember I'm doing an EPR. Electric charge, however many coulombs an electron has, a minus because an electron is negative. It's in a magnetic field, so I'm talking about an EPR. Obviously, the interaction has to do with the theory of relativity because there is a speed of light in it. So I know that whoever solved this had to use the theory of relativity, by the way. Just like when I see an h bar in the expression, any expression, whether explicitly quantum mechanical or not, that has h bar in it, is a quantum mechanical derived expression. It has to be. Anyway, so just a little factoid. You can tell people that you're smart, but that's good, right? Okay, and then of course, the magnetic field, B is the strength of the magnetic field. We assume that it's in the z direction just because that's easier, especially because we like to use a basis when we like to use a basis in the z direction. Okay, so let's look at the time evolving SX operator, which will be e to the I, and the terms in t over h bar. Sx at time 0, which we've already done. God, what is it? H bar over 2 plus minus h bar minus h bar over 2 minus plus. Right, not bad. It's just, now what the hell are we going to do with these e to the I h t over h bar? What do we do with those things, right? Okay, well, again, we can do that deal up there, but let's use the Heisenberg equation of motion. Okay, so I'm solving for the change in the x operator over time. And it's 1 over IH bar commutator of Sx of time. Again, there's my problem. I need to know the commutator, and I'm assuming that the Hamiltonian is time independent, which it is. I don't see time in here, so it's time independent. Let's see here. Okay, so I want to show you, here's the number one Slick Willy trick. And you have to have a time independent Hamiltonian, but basically that's, at least for what we're going to do in here, that's always the case. So let me write all this out. That's why I wrote this here. This is awful because I'm going to spend a tremendous amount of time writing the same thing over and over and over again. Now, remember, I also pointed out that this is where the book drops that t minus t naught. And I think they literally did that to save ink. Okay, so now I'm just permuting the operators. And there we go. Now, again, one of the big lessons here is all operator, 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 operator. I have 4 operators in a row. And it's great if we can rearrange the order for some convenient reason, but you can't unless you have some extra information. As it stands right now, this is what it is, and we'll figure out how to deal with it. Or if we're lucky, maybe there's some rearrangement we can do. And guess what? There's some rearrangement we can do. And that is, let me, here and here. The commute. Okay, when things commute, again, commutation or lack of commutation has tremendous implications. It's so many I can't even name them all. And that's why I keep saying I hate papers that say, oh, the operators commute. I know what that means, so what? It means you can change the order, right? This, that, minus that, this is 0. So this, that is equal to that, this. Okay, so what that means is, oh God, now I've got to write all this damn thing again. Oh, I hate this. So I explicitly explicitly try to avoid doing this. And I'm gonna have to, and heads up, I got to do this one more time. I'm gonna write all this stuff out one more time. And by the way, I showed you this, I showed everyone here, I showed you this trick last night, I just didn't prove it. Okay. Again, knowing that you have to be careful about the order, this ends up being e to the I. So you have to just double check that you're not messing up the order when you do what I'm doing right now. Notice that I've got a fully time independent. Yeah, that's right. Sorry, I was freaking myself out. For a weird reason, we'll see in a minute. Okay. This is on the left on every side, right here. And then it has to be in front of the H. And then this has to be to the right. It is. And it is. So I just factored. Again, I've taken all of these steps to make certain that when I factor something, that I haven't written AB as BA, right? You can't get the order wrong. Okay, then of course this is e to the I H T over H bar. And now we have the commutator in the time independent. Again, H was always time independent. Okay. Okay. So the point of this is that Sx, the time evolving operator, which I don't know what it is, now has a bunch of stuff, now has a commutator that is not evolving in time. That, I'm not trying to, the Sx of time is not in here because I have no way of knowing what the commutator is when I don't know what the innards of the commutator are. But now I do know. H is basically Sz. H is Sz, and Sx is Sz at time 0. I should have done that, right, now that we're talking about time evolution. Sc, right, which is h bar over 2 plus plus minus h bar over 2 minus minus in direct notation. I know what that is. Sx, h bar over 2 plus minus minus h bar over 2 minus plus. Now I can do that computation, and by the way, of course, it's going to be minus Sy. Yeah. And then you got these damn things. Anyway, here, let me go ahead and write it down. Continue on. And you may have noticed also that I did this, I actually did part of this in that handout. So the handout I handed out two classes ago, or last class actually is part of this problem. Anyway, I did it here myself, so let's see here. Where am I at? Okay. Now, I happen to know, and hopefully you remember from slightly less than a month ago, this is, where is H? Oh, if I abbreviate H as where the angular frequency, is that right? Am I messing up? Where is, I forgot how I put the Hamiltonian when you use the angular frequency. I spent a bit of time on that, showing how the Hamiltonian, as a function of angular frequency. And I did that just to not have so many damn constants everywhere. Where the hell is it? Oh, here we go. I just want to make sure. Yeah. Okay. Sorry. Okay, the angular frequency is, I guess, minus dB over MC. Okay, so what you end up with is constants just factor out. Let's see here. And this ends up being minus I. Okay. So there we go. Okay, so therefore, okay, so I'm just writing this damn thing down again. Okay, it is minus. Okay, that comes like minus, right there we are. Minus IH. I just put the angular frequency out here, and you can see that it cancels out a little bit easier. Okay, then I still got the E to the I, kind of wish these would go away. You'd hope that maybe there's some slick way of making these go away. There's not. And that's okay because it'll be obvious what happens next. Okay, so what's this? Unitary operator, the Y operator, unitary time evolving operator.
It's just SY.
That's not just SY. The time evolving SY. Right now, SY does not time evolve, as we have seen that so many times now. If it commutes with the Hamiltonian, then it would not evolve in time. But just like XX, SX does not equal 0, neither is SY. Only SZ would commute with the Hamiltonian, because the Hamiltonian is SZ, basically. Okay. It bears repeating. Okay, now guess what? If we had done SY, this is what you would have got. Solve that.
So,
That?
we are doing from spin, so in the case of EPR, we are saying that only the SZ will change, not, there's no time evolving in.
Well, now hold on. So what we've done is, all right, so we're talking about an electron, so I have to, I'd rather say that we're doing proton NMR because that's what everyone does. Since I talked about an electron, I have to say that we're doing EPR. It started out in the started out aligned with the magnetic field. The magnetic field is up and down, which we call Z. But what I'm going to do is I'm going to knock it over into the SX plus direction, just because why not? And then I'm going to query how everything changes by specifically calculating the average of Sx of time, the expectation value of Sx of time, and Sy of time, which the answers are here, because I did this in like the Schrodinger picture, right? Remember, when you see an expectation value, remember that you have to have defined for what state, right? So every expectation value is dependent on what state that is being investigated. And I specifically set this up to be in the Sx plus direction. Okay, to get there, I have to work this out with the Heisenberg picture. I have to figure out what these operators are. Once I have the operators, then I'm going to do this again. It's just I have a time evolving operator. The ket will not change in time.
I got it. So we talking about the S.
We bent it over in the Sx direction.
Then there's no component in the Y, right?
Not at first. Not at first.
At zero.
At first, the component in the y direction with sine of 0
Yeah.
is 0. It all makes sense, right?
Yeah.
Right, but you gotta wait for me because I'm still trying to prove it just with this alternative picture. But now remember, I'm still just trying to get to the operators. Then we have to use them. But if I run into a problem, then what the hell do I do? This depends on Sy, and Sy depends on Sx. But Sx, Sx I have to know Sy, but I have to Sy, I have to know Sx. Is it hopeless? What do you think?
Well, no, right? I mean,
And
well, it's just based on the fact that we know that, like you take an EPR before you Fourier transform it, right? It looks like the decay cosine function, right? So we know that it evolves in time like an exponential.
Well, sure. I mean, we know that.
So we're going to solve this somehow to like see how it varies in time and we can get an exponential out.
Well, sure. I mean, just because we can't mathematically model something doesn't mean that thing doesn't happen, right? So what I'm wondering is, are we smart enough to solve this? That's the real question. Now,
Constant derivative.
take time zero, then you can.
Real integral derivative equal to something.
well, just look at the handout I just gave. This is what I solved. So this is solved in the handout. Let me, so I'd have to spend an entire lecture solving that, and I didn't want to do that. So let me give you a nuances on how you do this. Now, and I also want to point out, these are the equations of motion for a spring. You will run into the equations of motions for springs in a tremendous number of things that are not springs. So, and of course, if we can't mathematically solve the motion of a spring, then how did we send a rocket to Mars, right? So yes, it's solvable. Let me show you, let me get you started on it, and then you just read the handout, because it is actually pretty awesome. Okay, now I'm going to start here. Okay, what I'm going to do is say Sy of t is, it's not hard, it's just that you can get a little bit like, okay, therefore, I'm going to take the time derivative of y, which is the double derivative now of x. But from here, let me make sure I didn't just mess that up. Yeah, there you go. Okay. Okay, therefore, there we go. Now you can solve it. The double derivative of a function is equal to minus angular frequency squared times the function. Or you can do this if you're more mathematical. Double derivative of the function is equal to minus angular frequency times itself. I know I'm using the board funky, but okay, now heads up. We've run into this differential equation before, this double differential equation. I even solved it in class with just, dy dx anyway, so now it's ds dt, but whatever. Any clue what the answer is? Okay, here's a hint. Think of the letters A and B. Huh? Free wave. What's the free wave solution? Right, the Schrodinger equation with no potential energy, Does it look like that? Double derivative with respect to x is equal to the energy times itself. I better try to use, yeah. Ta-da! That's the solution. Okay, now you got some more complexity here. A and B are like, what the hell are those? All right, now when you are solving differential equations, you always have to have, you have to have more information. You have to have a boundary condition, which, by the way, is the same thing as like the limits on an integral. Those are kind of equivalent, or not kind of. I think they are exactly equivalent. You never really know what an integral is until it has limits. So anyway, okay. Now in our case, so what's A and B? What are they? All right. What you do, you know that S. Now this is incredibly simple. Okay, now the derivative is equal to now remember the operator sy is h bar over 2, no, h bar over 2 times I? Plus minus?
There's only an I in the second term, right?
No.
I think so.
No.
Yeah,
There's
yeah.
that's why is this, right?
Yeah.
Right? Oh, anyway. So you know what this is. We wrote all these out a while ago. Plus minus I, minus plus I. Anyway, we've got all those worked out. Okay. All right, so anyway, what you find then is, so when you have those, and the handout does it, unfortunately you run into a whole page of algebra. It would take me about 20 minutes to go through all the algebra. What you do is you solve for A and B, and then you make e to the I, e to the minus I, cosine plus I sine, cosine minus I sine. It's just a bunch of algebra. It's really not too bad. It's just kind of complicated. And again, I've done all this for Sx, but y would be the same mathematical principles. And everything's out of phase by pi, which is a fancy way of saying that turn all the cosines into sines and all the, and vice versa. Okay. And the last bit, I'm almost done. So, therefore, it's x plus which is what we're trying to do. Remember, these are not evolving time. What that is equal to is now, hopefully you recognize that that's just h bar over 2. Sorry. Minus. Okay, and this is h bar over 2, which is what we solved Oh, it's right up there. Because heads up, of course. What's the projection of Sx into Sy? It's 0. Right? So if you look at so for one, you know enough Braun-Ket notation to solve this. When the state is in the plus Sx direction, the component in y is 0. And again, you can figure this out with all your Kets and Bras and all that. Or you can look at this graph and you can see that clearly the projection into the y-axis is 0. The projection of Sx is 1, and of course the x operator spits out h bar over 2. Then of course, for the same reason, what you get is h bar over 2 sine, which is exactly what I have up there as well. So it totally worked out. So I did all this stuff. Now, once I got to this part, it's in the handout. I've given a really broad, this is a little broad, right? So just look at the handout because again, this would take me half the class to do this. Sorry, no meeting?
No, not today.
Okay. It doesn't matter, I still need to be on time, all right? But anyway, that's it. Not too bad. You know, you can rewrite all this. It's mostly algebra, especially with that handout. That handout, I think, would help quite a bit. Yeah, the only thing that I spit out at you is this. Like, okay, this gets me there. But also recall, it was like the first week of class, I showed you how to, you know, if we were in math class, how to solve that. And I did that because this SOB comes up all the time. And as I mentioned, it's actually the equation of the spring.